Hey everyone, Katrina here, and today I'm going to show you how to solve trig equations. Be sure to subscribe for more videos like this and watch to the end to see all the examples. Okay, so this is actually a very exciting video. Trig has so many different complexities, and today I'm going to go over everything. This will be a complete crash course how to solve trig equations, and we're just going to go through a bunch of examples so I can show you all the different cases and how to set up these problems. Essentially what we're doing is if you have some sort of trig function, let's say for example cos theta equals to some number, let's say a over b, for example, where a over b is our ratio and theta is our angle. What we're going to be doing is we're going to be solving for the angle given a specified ratio. And we're going to explore different methods how to do this. Okay, let's dive into our first example to see how this is done. So first of all, we're going to consider some function cos theta equals to -1 over root 2. Okay. So we're going to go through this whole process and everything we need to know. Before we get into this example, we're going to write out all the trig ratios that we have. So we're going to use that as a cheat sheet as we go forward. So we have that sine theta equals to y over r, cos theta equals to x over r, tan theta equals to y over x, and we have our reciprocals. So we're just gonna reciprocal means you're taking 1 over the value, so we can write those out by flipping the ratio. So the reciprocal of sine theta is cosecant theta, and that will be r over y. Reciprocal of cos theta is secant theta, which equals to r over x, and the reciprocal of tan theta is cotangent theta, which is x over y. Okay, so what is actually going on here? So other people know this as SOHCAHTOA, which you can use when you have a right angle triangle. So y, we'll just write what it's equivalent to. So that could be, for example, like your opposite over hypotenuse. Cos is going to be your adjacent over hypotenuse, and tan will be your opposite over adjacent. I like writing it in terms of y, x, and r because if we're working on a unit circle, I find it's a bit more intuitive to think, okay, what's my x-axis, my y-axis, and then r is my radius, which sweeps out my circle. And then here you're just going to take the reciprocal for that side. Okay, so that's step 1. This is going to be our huge cheat sheet, which is going to help us through all these problems. So make sure that you always have this ready when you're solving trig equations. Okay, how are we going to do this? So step 1 is you always want to write out your unit circle, or your grids for it, circle, and define your cast rule, okay? So I have individual videos talking about all these aspects, so be sure to check out them if you need more information on ratios or on cast rule. And in this video, we're going to just dive through everything all together. Okay, so we're setting up our unit circle. Okay, and what do we need to do here? So there's actually one more piece of this problem that we have to add. So we're trying to solve this. So we're trying to solve for theta. And since functions are periodic, they will repeat over their period towards infinity. So we have to define a domain. So we're going to say that theta has to be less than or equal to 2 pi and greater or equal to 0. So this is kind of the typical one that you use. That is like your standard one, quote unquote. And we can see that 2 pi will sweep out a full circle. And let's write that out over here. So we're going to write out our unit circle. So we're following our domain. We're starting at 0. We go to pi over 2. Then we have pi. And then down here we have 3 pi over 2. And moving back, we've got 2 pi. So just some terminology. This line over here, this is going to be our principal axis, and then we're going to be moving counterclockwise around this circle. Okay, so what do we do next? We said define our cast rule. So our cast rule, we're going to start in the fourth quadrant here. We write C, A, S, T. The cast rule tells us which quadrants are going to be positive or negative. So we can write out our quadrants. This is 1, this is 2, this is 3, and this one here is 4. So now we've defined our unit circle, we have numbered our quadrants, and we have our cast rule. So our cast rule tells us where they're going to be positive. So the A stands for all, so all ratios are positive. S stands for sine, so only sine is positive in quadrant 2. T stands for tan, so only tan is positive in quadrant 3. And C is cos theta, so only cos is positive in quadrant 4. Okay, so we've done our unit circle and our cast rule. So 2 is we want to set up our ratio on the circle, or I'll just say on the grid, in the appropriate quadrants. So which quadrants is it going to go to? So which quadrants? So that's kind of important. So we want to put our ratio on the grid, and we have to determine which quadrants is it going to lie in. Okay, so following our cheat sheet over here, we know that the ratio for cos is going to be x over r. So that means that our x value is going to be -1, and our radius is going to be √2. So radius, just so you know, can never be negative. So r cannot be negative. It's always positive, so you have a chance that either your x or y value has the potential to be negative, but never your radius. Okay, so where are we going to put this on our quadrant? So we can see here that we have a negative ratio. So we need to determine where is cos negative. So we can see here that it would be positive in the A quadrant for all and the C quadrant for cos. So that means we need to put it in the 2 quadrants where it would be negative. So we put it here and we put it here. And then here we have to follow what I call the bow tie rule. So when you're drawing things on the quadrant, make sure that you draw your triangles like this with its vertex in the center, and it looks like almost like a bow tie. I don't know if that's the official word, but that's what I like to call it. And that kind of helps us make sure that we draw our triangles with the correct orientation. Then you can kind of just draw it down here and here. Okay, so we've set that up. Let's fill in our x and y value, x and r values. So we know that x is going to be -1, which makes sense here. And then our r is going to be √2 and √2. Okay, so this is also has to be a right angle because we're creating right angle triangles. Okay, so what can we do next? So next, step 3 is, we'll just write that over here. We want to define our, what I'm going to call our internal angle. So the internal angle is going to be the one that's found kind of within our triangle. So this angle over here and this angle right over there. So this is where we might need to use special triangles. So if we have a special triangle, then we definitely want to use that to help us find an exact solution. If you don't have a special triangle, you might have to use something like Pythagoras theorem, or you might just have to use your calculator just to plug in the ratio. Okay, so in this case, we do have a special triangle. Again, if you need some more review on that, please check out my video on special triangles and subscribe so you get notified when I drop some new ones. So here, this is our 1, 1, √2 triangle. So that means this one, and this one's going to be 1, -1. And what is our angle? So this is an isosceles triangle. This angle in here, our internal angle, is going to be pi/4. So both of these kind of internal angles within the respective triangles are pi/4. But we have to keep going. So our step 4 is going to be determine theta 1 and theta 2. So what are the actual angles that we're looking for? So recall that when we're solving for angles, we have to start from our principal axis and move counterclockwise. So that means we start here and we want to go and find this angle. So we'll call this theta 1. And then let's switch up our color. Let's say now for theta 2, again, we're starting on our principal axis. And we need to go, maybe we'll show it from here, all the way around and find, our theta 2. So we'll call this theta 2. So it doesn't matter where you start as long as you start on the principal axis and you're trying to determine what is that circle that you're drawing, how much of the circle are you sweeping out, what is your angle. Okay, so I'm going to let you in on a little bit of a trick. So let's say that we have our unit circle set up over here. So we have our angles, so 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay? So how can we find our angle? So let's say that we have, our bow tie rule all set up here, and say we'll just call this small internal angle here alpha. So we've got alpha for each one. Okay, so how can we find our theta? And our theta, like I said, is going to be when you start from the principal axis to whichever line you want. So here would be 1 theta. If we want to look for this angle here, that would be theta, for example, and so on. So what is the trick of finding our actual theta? So that's what I'm going to tell you. So in quadrant 1, your theta is just going to equal your alpha because you calculate your angle from your principal axis, highlighted in yellow. In quadrant number 2, you're going to use pi as a reference point. So you're going to do pi minus your alpha, and that's going to give you your theta, right? Because pi would be all the way down, and then you're subtracting this little alpha to get your theta in red. In quadrant 3, we're going to do the opposite. We're going to do pi as our reference point plus our alpha, and that's going to equal to theta, right? Because if we draw this all the way down, we need to get to here. And then lastly, in quadrant 4, we can do use 2 pi as our reference point. So we would do 2 pi minus alpha, and that's going to give you your theta, right? Because we want to come from principal axis all the way around to this blue line over there. So you can see it's basically a full circle, which is 2 pi, but then we just need to subtract this part over here to get what our theta is going to be. So sorry if that looks a little chaotic, but definitely I'll highlight the equations that you can use, and that's just a good rule of thumb, which will help you solve these problems. Okay, so for our problem over here, our question, let's go ahead and do step 4. So I'll just say, oops, sorry about that. So we're doing our step 4 over here. So we have that our alpha in this case equals to pi over 4. So that is our internal angle, will be our alpha. So, okay, so our first one is in quadrant 2. What does our equation say? It says that pi minus alpha equals to theta. So that will be our theta 1. So in that case, we have pi minus pi over 4. Let's find a common denominator. So we have 4 pi over 4 minus pi over 4. So we have 3 pi over 4, and that is our theta 1. And what about theta 2? So theta 2 is in the third quadrant, so we can use this equation right here. So then we have pi plus alpha equals to our theta 2. So then we have pi plus pi over 4. Let's find our common denominator. So that means 5 pi over 4 is going to equal to theta 2. So we have answer 1 and answer 2. And then the last thing you want to do is 5, check your domain. So just be sure that both of your answers fall within your domain. So we know our domain is theta has to be between 0 and 2 pi. So just be sure that we have here 3 pi over 4 and 5 pi over 4, that they both fall within this domain, and we can see that they do, but it's always good to check. Okay, so that was example 1. I really took you through a step-by-step process, gave you some great equations that you can use as a cheat sheet to help solve these trig equations. Now that we're a little bit more comfortable with this, let's go through another example a little bit quicker so we can apply everything again to make sure that it sinks in. So again, this one we want to solve for theta, and we have sine theta equals to root 3 over 2, and then we have to state our domain. So we're going to say that theta, again, is going to be in between 0 and 2 pi inclusive. Okay, so let's go through our step-by-step process. So recall step number 1 all the way up here. So step number 1 is we need to write our unit circle and define our cast rule and just set up the structure for this problem. So let's do that. So we got our quadrant 1, 2, 3, and 4. I literally recommend doing this every time. We got C, A, S, T. No harm in doing that. And then let's set up our angles for our domain. So we've got 0, pi over 2, pi, and 3 pi over 2, and then finishing up our cycle, we go back to 2 pi. So again, I'm solving this in radians. You can solve this in degrees, but I find that most high schools, universities will usually use radians at a higher level. But if you have questions about degrees, I have a video that explains how to convert between radians and degrees, so don't worry about that. Okay, so we've done our step 1, we've set up our quadrants. So now let's go ahead and do step 2, and let's double check what we said there. So we said step 2 is we're going to set up our ratio on the grid and determine which quadrants it falls under. And remember the bow tie rule. Okay, so let's remember our ratio. So sine is the same as y over r, which again would be your opposite over hypotenuse. And it is positive. So following our cast rule, which quadrants would this fall under? So we can see that sine would be positive under the all quadrant and under the sine quadrant. So let's go ahead and put our angles there, triangles there, again following the bow tie rule, which I mentioned above. And please note, these aren't exactly drawn to scale, just doing my best out here. But you get the gist of what's going on. Okay. There we go. So we've put them in the quadrants, and now let's go write out their values. So y is the vertical one, so we have that this is root 3, this is root 3, and then our radius, remember radius is always positive, equals to 2. Okay, so step 3 now is, I think we want to use, define our internal angle alpha and look for our special triangles. Wow, it looks like we have a 2 and a 3. This is really giving me special triangle vibes. So this is 1 over here and -1 by our special triangle. And let's determine our internal angle. So we know this special triangle across from root 3 is going to be pi over 3. So we can fill that in both cases. If we want to fill the whole triangle out, we can, just for reference. So we know this has to be right angle, and then this one would have to be pi over 6, because the total internal angle of a triangle has to be equal to pi, or 180 degrees. Okay, step 4 is we need to find our theta 1 and theta 2. So we can see that on this domain of sweeping out one full circle of 2 pi, we're going to have 2 possible solutions for theta. So we want to find theta 1 and we want to find theta 2. So again, this one over here will be our theta 1, and then this one over here is our theta 2. So let's go ahead and remember our handy dandy little equations over here that help us use our alpha and our reference point to find our theta. So theta 1 is in quadrant 1. So what do we know? We know that our alpha equals to our theta 1. Theta 2 is in quadrant 2. So that means that pi minus alpha is going to equal to our theta 2. So let's fill this in. We said that here alpha equals to pi over 3. So we already solved for theta 1. And for theta 2, we've got pi minus pi over 3. We can add our common denominator. So that means it will equal to 2 pi over 3. And there you have it. We have our solution for our theta 1. And we've got our solution for theta 2. And like I said, as like a final step, you can always go back and just make sure that you check that theta 1 and theta 2 fall within our domain between 0 and 2 pi. And we can see through observation that they do. So just a little extra trick. So during one cycle, so one period, which is one sweep of the unit circle, which is 2 pi, from 0 to 2 pi, you will have at most 2 solutions. Okay, so if you think about the cycle, let's just say of the sine, and we want to know when is it going to reach, like have a value of, what do we say here? Like 3 pi over 2. That's probably going to be somewhere over here and over here. So if we draw like a little line across, we can see that we have 2 angles. So we're going to have an angle over here, or theta 1, and then over here, sorry, that's a bit blurry. So we'll have 2 angles, so here and over here, where that side length ratio exists. So that's why we have at most 2. There is a caveat. You will have one solution if your ratio falls under one of the axes of our grid. So meaning that if you're at, for example, 1, so you're in one period, you'll only reach your maximum of 1 once, and that will happen at your pi over 2. And then your minimum, a value of -1, you will only reach once, and that will occur at 3 pi over 2. So if you have a value that falls either at pi over 2 or 3 pi over 2, you will only have one answer, because that's either your maximum or your minimum of the function. So just be aware of that, but otherwise usually expect to find 2 solutions. So don't stop after you just found one. Make sure you use the cast rule and find all the quadrants where it would be either positive or negative according to your ratio. Okay, so with this being said, here at the end, I'm just going to show you one more example, just to kind of show you another little case. Okay, so what if we have, like I said, sine pi over 2? Okay. What if we have sine of, I think I gave the answer away there. What if we have sine equals to 1? Sine theta equals to 1. What is the angle? Well, I think I just told you, but let me show you what that looks like on our unit circle. So we are setting it up 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. 1. We know that sine, again, is y over r. So we can kind of think of this as 1 over 1. That our y equals to 1 and our radius equals to 1. So say this is 1. This here is going to be our line. So we've put it onto our unit circle. Hey, but what angle is it? You're not really creating any triangle. So kind of like what's happening. So right away you can see that it would just be pi over 2. Because it's literally on the line of pi over 2. It might be a bit confusing sometimes because you're like, wait, I didn't really draw a triangle. Essentially, you compress your triangle so much that there is no x value. You just have a vertical line. And this is where if you consult the sine function that looks like this, sine equals to 1 at pi over 2. And that's the only time that sine will equal to 1 on this period between 0 and 2 pi. So the answer is simply just going to be pi over 2. So you would say even when like theta is an element of 0 and 2 pi, you're only going to have one value for theta. So theta 1 will simply equal to pi over 2 because there's no other times on this cycle when this happens. So again, if you ever get that sine equals to 1 or -1, it's always nice to check your graph. So at -1, it would be at 3 pi over 2, and here this would be at -1. So that's just something to look out for, because I remember I was a little bit confused when I first learned about that. So rely both on like your unit circle, but then also remember your actual graph that you're working with. And if you know like the main properties of your sine, cos, and tan functions, then this can actually render the process a lot easier down the road. Okay, so if you enjoyed this video, please drop it a like and comment any questions that you have. I look forward to hearing from you. And if you want to learn more about Trig, be sure to subscribe because I've got tons more videos coming your way. See you next time.